Hi, I'm Nicholas Corell, and this is Generative Models for Robotics. Before we start, let's have a brief look at where we are at in robotics. On this slide, you see a lot of exciting things from the past 20 years in autonomous driving on the left and in manipulation to the right. What happened in autonomous driving was that DARPA, the Defense Agency for Research in the US, has set out a competition in 2004 to drive an autonomous car from Los Angeles to Las Vegas to the desert. And although the first competition was really a big flop, people only got a few meters sometimes with their vehicles. In 2005, just 1 year later, the Stanford team has won the competition with their car Stanley. And then there was another competition 2 years later. This is, I think, Carnegie Mellon team. And 20 years after the first success, we have the first commercial ride with Waymo. And also Nuro is deploying. And so since many companies have started to offering commercial rides. So the point is really, from something really wild and crazy, it only takes 15 years to get from nowhere to commercial reality. Now in humanoids, DARPA has done the same thing in 2015, and also this was a big flop with the robots falling over and breaking things and not really performing very well. But if you think about this timeline, we should have the first really successful commercial deployments in 2030 if you just compare with the autonomous driving. There's another challenge, the subterranean challenge, which the CO Boulder team has won third prize with Chris Heckman and Sean Humbert and others at CU. This is happening still. But then the very big open challenge is manipulation, where we have many competitions at IROS conference, the Amazon Picking Challenge. This is the first team that won it, the team from TU Berlin. Then there was an industrial assembly challenge at the World Robot Summit in 2018 to assemble a widget like this. This has been won by a Danish team. And there are some companies in that space that are successfully selling manipulation. This company was sold to Ocado some years ago. Right Hand Robotics is still independent. But now what really changed everything in 2024 is an explosion of humanoid robots 9 years after this DARPA competition, and these things are becoming available for relatively little money and challenge the robotics field to implement autonomy and especially manipulation. So manipulation is really the last big challenge. If you think about all these autonomous cars being able to move things, or autonomous carts inside buildings, what we don't have is anything that really picks up individual items and places them on pallets, let's say, then manufactures the items, ships them, retails them, maybe processes them at your house, and then at the end recycles them. So I have some example companies here that actually do these things, but they use very specialized equipment and tools, and they are far away from how humans would do that. And so we still have a lot of humans in the loop who have to do all the manipulation that is involved here. Now, the good news is we have a lot of recent breakthroughs, and this is what the class is about. So first, you all know ChatGPT and other tools like it, which are known as large language models, which can provide common sense knowledge to robots that was previously not available. So, for example, if a robot would want to know where it could get a sandwich, it could ask ChatGPT, and ChatGPT would say, why don't you check in the fridge in the kitchen, or buy it from Subway. Oh, by the way, the next Subway is so and so far away. And we have now a whole new level of intelligence at our fingertips to make these humanoid robots smart. ChatGPT is not just text, but you might have noticed that it also allows you to upload pictures. It understands many of the things that are on the pictures, and this is called a vision language model. So we can use these tools now to have a robot walk into a room and actually find items that it wants and possibly even pick them up. So also this is something we will talk about in this class. And finally, there's another axis here, which we will not cover in this class, which is reinforcement learning and model predictive control, which is actually now working thanks to massive GPU based acceleration, much like we use for the transformer models and flow matching that we will study here. I have a lot of content on our blog, which is medium.com/corellab. So the students taking their in-person version of this class are blogging their homeworks there and their final results. So if you check this out, you will find probably very recent results and tutorials in this area. So one of the things we will work toward to is so-called vision language action models. And here the idea is that you can take images and text description of the task that you want, plus the current state of the robot. So in this case, it will be all the joint angles of this humanoid, and it will generate the next best guess at where to place all the robot's arms and legs in this case. So let's play a video. This is from Tesla from, I think, mid of 2025. And what you see here is tasks that the Optimus robot at Tesla is executing based on the text prompt that you see here in the bottom. So here, pick up the brush and dustpan, clean the table, and the robot is executing this using for so-called vision language action models. So as of right now, the best architecture for such a thing is a vision language model that has a flow matching action head in front, which is a different generative model. This is also why the class is called Generative Models for Robotics, not just Transformers for Robotics. And then doing this in the frequency domain. So this class will cover most of what you will need for actually all that you will need to build such a model from scratch, and also train models based on pre-trained examples from the internet. There's a little disclaimer. The robot that you've seen has been working very well. It's a video that they took, and of course they could make choices. I want to show you real quick a little snapshot of what you can get by training a VLA on a simulated data set. So in this case, it's the Libero data set, which has 130 different tasks, which are very similar to what you see here, pick and place of random objects, essentially. And in this case, they have 1,693 episodes. That means 1,693 complete demonstrations of one task, like let's say one pick. And these contain 273,000 state transitions where a picture is given and you have the resulting action that the robot takes. All of this is 34 gigabytes worth of data. And now we have trained two models here. One is called Small VLA. That's something we will study in great depth here, which is a very small model. So that means you can actually train and fine-tune it on, let's say, Google Colab. In this case, training this would take 4 hours on an A100 with 40 gigabytes. And you see what it does here. And you see it doesn't really work very well, but eventually it will pick up something. Let's play this again. So you don't have to, and you see it kind of grabbles around and kind of closes its gripper a little prematurely. But now you can also train this on Pi0, which is an open, it's not open source, but partly open source. And you can download the trained weights and fine-tune against it. And so this is Pi0 Fast, which is a 2 billion parameter model, so it's 10 times as big. And training and fine-tuning this, it's not training, sorry, fine-tuning this on the Libero dataset takes 19 hours on an H100 with 80 gigabytes. And you see it works a lot better. Now, you shouldn't forget, this is really highly correlated data. You have simulation data, which doesn't have like, lightning effects or friction, things like this simulated too realistically. But you also have only this exact camera angle here at which this is done. If you change that camera angle slightly, it might not work as well. And so what this has all created is a very big hype where people started putting things online. and not online, but in, customer facing. And this is Lucky Gold Star LG, who has released a household robot at CES 2026. So this is a very common task in VLA demonstrations. Usually you need like 2,000 or 3,000 demonstrations of just this task, of just using the same piece of cloth or t-shirt or something. And the robot is actually here being filmed at CES and is actually unable to do that. So this works with Pi0 Fast. In this example, they report 85% accuracy. So that means it doesn't work for all of these tasks that you see here. And likewise, this LG demonstration is subject to failure, and then the robot just doesn't know what to do whatsoever. So what this tells us is this is an open topic. A lot of research is needed. There are many, many ways of improving this and contributing to this field. So this class should create the baseline for you doing that. So I want to conclude with where all of this fits in, and I came up with this slide here where I place classical robotics in the bottom left, and I have an axis here which is computational performance or speed. And you could argue that classical robotics is rather slow if you want to solve all the equations, and that reinforcement learning is doing this much faster. So once you trained, let's say, a controller for an inverted pendulum, the actual control can be computed at, let's say, 1 kilohertz, while solving the equation might have taken longer in the past. Now it works in real time, but for a big humanoid, it might still be faster to do reinforcement learning, let's say for walking. And what we see is that there are techniques where the classical robotics gets taken into reinforcement learning using differential dynamic programming or ILQR. You can, for example, generate experiences for RL to train, but this is not what the class is about. We are working on this angle here, or this axis here, which I label as generalization. And the idea is that VLAs can possibly, in the future, replace everything we know from classical robotics by learning from examples. And so what you will learn is how all of this works and where we're currently at. But in reality, what happens is people are using classical robotics techniques as much as they can. They're augmented with LLMs, with VLMs, and we will talk about all of this in this class. And really creating a controller that really only uses snapshots of what the robot currently sees, what it has done in the past, and what the text input is to create action output is really a futuristic vision. But this will give you an idea where all of these different techniques fit in and allow you to leverage them.